Calculus lesson on optimization. Okay, guys, let's get started with this. Well, here's a procedure that we should generally follow. If picture is not provided, you should draw a picture. Okay. Sometimes the question calls for certain situations, and sometimes you got to draw your own pictures. And then you would want to write a general equation based on the picture or given information, and write an objective function, the equation that you wish to like maximize or minimize. It's the desired quantity, right? And then fourth is to differentiate set equal to zero. And generally, when you do that, you will be maximizing or minimizing that value, right? Hence the optimization. Um, Generally, the questions don't try to trick you into it, but you should check it nonetheless, okay, to make sure that it is the minimum or the maximum, relative min max, that is, right? And then for the fifth step, whatever critical value that you've found, you should check to see if you got the right answer by doing sign analysis. And also, really important, eliminate answers that are not in the domain, right? Okay, the first question is to find a point on 6x plus y is equal to 9 that is closest to negative 3, 1. In this particular case, you're going to have to draw the picture on your own, right? Okay, so I drew the picture ahead of time. And then using the intercepts, obviously my y-intercept is 9, and my x-intercept, when you set that equal to 0, is 9 over 6, which is 3 over 2. So I draw a line over here. And then we got negative 3 ones over here, so we know that has to be perpendicular. It looks something like this, right? Now, it is possible to do this without using the calculator, calculus, but I think it makes it a little easier, right? So how to find this distance, guys? Right, we use a distance formula, right? And the distance formula may look something like this right here, right? Um, and then basically it is a square root of the change in x squared, which is from here to here, x minus 3, and the change in y squared, which is y minus 1. We got that. And this equation right here, guys, solving for y gives you this. Substituting into that, this is what we get. But there's something we should notice. Right? Instead of just rushing to differentiate this, right, which will leave us with half or something of negative half, copy that inside, and then whatever's inside, we take the derivative of. It's really a pain, isn't it? So it's important to sort of think about what's going on. Look, we're trying to minimize this, but the minimum value of the square root is the minimum value. Does that make sense? Right, right. Let's say, for example, you have the values 9, 4, and 16. If you square root all of them, that becomes 2, 3, and 4. So the smallest value still remains smallest. Does that make sense? Yeah. So all we have to do is integrate the inside. Now, think about this for a second, guys. If you had taken the derivative of this, you would have gotten half of the inside to the negative half, which is in the denominator, by the way, and multiply by the derivative of that, right? Okay, we're going to set that equal to 0. That's in the denominator. So only thing that matters is the numerator anyways, right? Right. Well, either way, that's all I care to do. Okay. So I made a little I already did it a little bit ahead of time. Okay. To minimize the steps involved. So that was it, guys. So note that the minimum value of f of x is also the minimum value of d of x, right? So I did the derivative of that, which yields this, set equal to 0, and I found that x is 45 or 37. And then plugging the x into the y value right here, as it turns out, it's 63 over 37. Therefore, those 2 points are 65 over 37, comma, 63 over 37. Okie dokie, guys. All right. Let's look at number 2. We have an open box with a square base and has a specific volume that's fixed, by the way. And we want to find the dimension of the box that minimizes the materials used. So we want to minimize the surface area. Is that right? Yeah. So we want to draw the picture, right? So remember that's open top, okay? What is that we really need, guys? Right? That's right. What we needed is the volume right there. Is 32,000 cc. That's the restriction. That's what it has to be. But the area is equal to what? It's the perimeter times the height. We'll give you the lateral area plus the base. Remember that from geometry? All right, guys. I went ahead and did some of this already, so I will save a little bit of time for you guys. Here we go. That's the surface area, guys. Right? We're going to minimize the surface area, which is, let's see, the lateral area over here. That one is like 4 times x, right? So x times y, that is. There are 4 of them. Plus the base, which is x squared. And the y, when you solve for that, is what? Y is equal to 32,000 over x squared. When you plug that in, we end up with this. So we're going to do the derivative. Okay, so and I went ahead and did that already as well. Let me just bring that up here, guys. All right. I just made it a little small so I could fit that in. There you go. Now, once we do, I set that equal to 0. See that? When you solve for that, I get x equal to 40. And then plug that into the y value. Sorry, this right here. Y becomes 20. So the ratio, so the dimension is what? 40 by 40 by 20. All right, but how do you know that this is the minimum? Well, uh, well, it's not quite as intuitive to see, but if you made this like really wide and very thin, right, you have so much area this way, it will actually be more. But it's hard to see actually if you don't have a good. Um anyways, so when you plug in the value here, guys, right, you plug in a little bit to the left of the 40. Let's say plug in, let's say, I don't know, um, 1 or something like that. That's a 2, negative 120,000. That's definitely negative, right? And plug in something big. I don't know. It's like a million. That's essentially 0 and very positive number, right? Yeah. So when something comes down and up, that value is actually the relative minimum value. Okay. And I believe I wrote down the conclusion as well. And there it is. All right, guys. I don't know if you guys would like this particular format, but I figured this was uh, sort of like make the video a little shorter and get all the information out there. Okay. All right. Here's the next question. A right circular uh, cylinder is inscribed in a cone. Okay. Height h and radius base r, and find the largest possible volume of such a cylinder. Okay. So I went ahead and drew that for you here, guys. But the key thing right here that you really, really have to recognize, otherwise it gets a little tricky, right? Is I would actually draw an axis right there and here, right? Okay. And you know that my height is h and my radius of the cone is r. So it has to go here. So the equation over here is equal to this. This is what some people don't know about this, but that's called the intercept form, right? It's kind of like if you think about what we did with conic section, that should make more sense, right? Let's say, for example, if y is equal to 0, boom, x has to be r. X-intercept, that is. Y-intercept is when x equal to 0, set that equal to 0, y is equal to h. Beautiful. Okay. All right. So we have this, and we are trying to maximize this. So you may be thinking, hey, wait a minute, let's solve for y and plug it in. Well, I suppose you could do that. I did a couple of them. And let's drag that up there. Okay, here we go. That's a little bit too big. That should be a good size. All right, guys. There you go. Now, if you try to plug this guys, alpha y here into this, I don't know about you, but that may seem a little tricky. It seems to be a little bit easier to replace x. Okay. Another way to do that is just draw this triangle and this rectangle. And you'll see that this triangle, and that triangles are all similar, isn't it? All right. So this is x, this is y, because that's x, that's y, right? That's r minus x, that is h minus y. Which one is the best? Well, if I compare the big triangle to this small triangle right here, this is what I end up with. And I realize that, with this one, it's easy to solve for y. Let's try this triangle. Then I end up with h minus y over x. This one is h over r. This one. So the x is equal to this. I am going to pop that in here. Yeah, I know it's slightly involved, but I think it's okay. Okay. Well, you guessed it. I went ahead and did a little bit of it. Okay. And let me just drag it up there. And let me walk you through what I did. Okay. By the way, all this time, if you are brave and you feel comfortable, you really should be trying this out on your own prior to listening to the lecture. So we have this question, guys. Okay. So I plugged in for x right here and I squared that, right? And I, hold on a second. Oh yeah, I messed up a little bit. That's actually squared. It really doesn't matter, right? So I guess that's probably the reason why I really didn't pay attention that much. But yeah, so if you square that and pull it out, that's what you get. But when you expand it out, you know it's h squared minus 2hy plus y squared. But you're gonna multiply everything by y, so here it is.